The excision axiom in singular homology has many meanings that are not apparent from the statement. Let me recall the statement first. So we have subspaces A, B in X such that the closure of A is in the interior of B and everything is in X. And then if we start with the pair XB and we excise A, then the inclusion induces an isomorphism. So it goes from X minus A, B minus A, and the singular homology of that via map induced by inclusion into the homology of XB. And the iso is for all n. So this is the excision axiom that we want to prove today, and we also want to understand its meaning. So one meaning is that we can compute singular homology of a space from smaller pieces of the space. But this is something that we deal with in a later video. Today we want to give the idea and the underlying reason for the excision axiom to be true. And the reason is that you can compute singular homology from small singular simplices. So you should think of that like you have maybe a metric space, and then you can talk about the diameter of the image of a singular simplist. And the statement is something like you can represent any singular homology class by a singular cycle that consists of singular simplices whose diameter, the diameter of the images of the singular simplices, is smaller than, I don't know, 1/10, something like that. So in general, we deal with topological spaces. We don't have a metric around. So let me formulate the idea of smallness in the topological setting. And that's the following definition, where we consider a cover of the space. So let U be family of sets in subsets in X. So cover always means that the union of these subsets covers the whole space, is the whole space, but actually we are requiring a bit more. We are requiring that also the union of the interiors of these subsets is the whole space. So in particular, if the J's are all open, then their union is all of X. And then we call a singular simplex n simplex in X. So I think the notation was Snx for the set of singular n simplices. U small if its image lies completely in one of these subsets. So if there is some index j with image of sigma is in uj. And the u small singular simplices, they generate a subgroup of the chain group of all singular simplices. And indeed, it's not just a subgroup, it's a subchain complex. So and we denote this by Cu star of X. This lies in the singular chain complex. So for now, I drop this decoration singular here. For us, C star X in this video is the singular chain complex. And C star Ux is the subchain complex generated by the U small singular simplices. Why is it a chain complex? Why is it a subchain complex? Well, if you take the differential of a singular simplex that completely lies in one of these subsets uj, then also the faces, so the n-1 singular simplices that you get from the faces of this singular simplex lie in uj, and therefore the differential in c star x restricts to a differential on cu star x. So it's really a chain complex. And maybe one picture to illustrate this. So if you have, say, cover U that consists of, let's draw the sets uj as balls. So we have here 3 balls from this cover U, and then we have a singular simplex, so a map from the standard simplex delta n to this space, and well, maybe take a different color here. So that's the image of this map, sigma. Then this is definitely U small because it lies completely in this subset. And if we have a simplex that looks like, I don't know, could be something like that. Then this is obviously not a U small simplex. So that's not in Cu star. And the lemma that's at the core of the excision axiom is that we can compute the singular homology from this complex Cu star of U small simplices. So let's call it the lemma of small simplices. And the statement is just that this inclusion of this chain complex into the singular chain complex is a homology isomorphism. Okay, I never used the term homology isomorphism so far. What I mean is that it induces isomorphisms in homology in all degrees. And in fact, a bit more is true, but this is something I won't prove. Let's put it here as a remark. So in fact, this inclusion is a chain homotopy equivalence.
So we defined what a chain homotopy is, but still we should probably say what a chain homotopy equivalence is.
Yeah, we haven't defined explicitly chain homotopy equivalence, but it's just the same definition as for homotopy equivalence. We have the notion of chain homotopy, and we have the identity map. So it's clear what a chain homotopy equivalence is. You have a chain map in one direction, chain map in the other directions, and both compositions that you can form are chain homotopic to the respective identity on the chain complex.
Mm-hmm. So we're really asserting that there's a chain map in the other direction here, but that will not be needed to just get the proof of the lemma.
Exactly. In the proof that I'm going to present, we will prove that this is homology isomorphism without explicitly writing down a chain homotopy inverse. But you could do it, explicitly write down a chain map that starts here and goes there, and both compositions are chain homotopic. It's a bit easier to just prove that's a homology isomorphism, and it will give us the excision axiom.
Both compositions are chain homotopic to the identity. That's
what did I say?
You just said both compositions are chain homotopic.
Oh,
period.
Yeah, chain homotopic to the identity. All right. let's explain why the lemma of small simplices implies excision. And that's not terribly hard. Actually, most of the work is contained in the lemma of small simplices. What's the cover? The cover is a very simple one. It just consists of two subsets. So let U be the cover consisting of B and X minus A. That satisfies the assumption of the lemma, because we have that the interior of B and the interior of the complement here, well, that's the same as the interior of B, and X minus the closure. And the assumption was that the closure of A is contained in the interior of B. Therefore, this union is all of X. So we can apply the lemma of small simplices to this cover U. We have C star of B minus A, and I want to rewrite this as the intersection of the singular chain complex of B and the singular chain complex of X minus A. Okay, if I write an intersection here, they all lie in the, you can think of these chain complexes as subchain complexes of C star X. So they're all in one chain complex C star X. You can form the intersection, and then the intersection is really C star of B minus A. And we can also rewrite the chain complex of these U small simplices, because in that case, these are, this is the subchain complex generated by singular simplices that either land completely in B or in X minus A. And actually, I should not say either or, because there might be an intersection, non-trivial intersection between these two sets, so it can actually also land in both. But there are in B or in X minus A the singular simplices, and therefore this chain complex is the sum of the singular chain complex of B plus the singular chain complex of X minus A. And as I emphasized, this is not a direct sum. This is just a sum within the complex C star X, because again, a singular simplex might, with its image, lie both in A or in X minus A.
That's why there's no circle around the plus.
Exactly. That's why there's no circle around the plus. So we have the chain complex, that's the domain in the excision map, which is C star of X minus A, B minus A, right? And by definition, this is a quotient. This is the quotient of C star, X minus A mod C star B minus A. So that's the, somehow forms the domain of the excision map. And the excision map is induced by inclusion, and on the chain level, it goes to the singular chain complex of XB, and this is the quotient of C star X by C star B. Right? And by definition, this is C star X comma B. Right? So this red chain map induced by the inclusion, this is the one for which we want to show that it is a homology isomorphism, because that's the statement. Now, we can rewrite this one here. I mean, that's actually the identity map that I'm just rewriting this as C star x without A, and now, as I said above, this is the intersection of B and C star x minus A. Okay, what we have written above, just rewriting this. Now, this is canonically isomorphic to, maybe scroll down what we had here, right? This rewriting. I want to bring this sum of chain complexes into play now. So this is the same here, canonically isomorphic to C star B plus C star x minus A C star B. Okay, so what's the name of this isomorphism? Never know.
It's got a name?
Yeah, it's like there's the first, the second, and the third isomorphism theorem.
Isomorphisms.
Noether
yes,
isomorphism theorem.
But don't ask me which one it is.
So it has a number.
Maybe the second. I don't know.
But it's a quite obvious isomorphism induced also by the inclusion of that into that sum. Right. Probably the third Noether isomorphism, something like that. Mm-hmm. Anyway, we're here now. Now this sum is just C star U. So let's write this. And this is also just the identity, but it's better to write everything as a map now. And on the bottom, you also have the inclusion induced by the inclusion of C star U into C star X. And of course, everything is induced by the inclusion, so the whole diagram of chain maps is a commutative diagram, and we have the identities, we have isomorphisms here. So the only thing we have to show to prove that the red arrow, the red chain map is a homology isomorphism, is to prove that this chain map star coming from the inclusion is a homology isomorphism, and that would prove the excision axiom. So the lemma of small simplices doesn't quite say that. It says that C star U into C star X is a homology isomorphism, but now we have these quotients. So let's figure out why star is a homology isomorphism, assuming the lemma of small simplices. And that's an argument that you should remember anyway, because it appears very, very often. Maybe let's keep star in the picture. So it suffices to show that star is a homology isomorphism. Here's how we do that. We embed this quotient here and this quotient here into short exact sequences of chain complexes. They start with the singular chain complex of B. Then we have C star UX, and then the quotient we're interested in. So by definition, since we form the quotient, this is a short exact sequence of chain complexes. And the other one is the one with C star X. So we have the maps, which are either inclusion or identity. And obviously, the whole thing commutes. And we want to prove that this here is a homology isomorphism. This is trivially a homology isomorphism, it's just the identity. And the middle one is a homology isomorphism by the lemma of small simplices. So why is the right chain map this one here? Why is this a homology isomorphism? And this is an argument that appears over and over again. It's a combination of the long exact sequence, its naturality, and the 5 lemma. And later on, this should suffice, right? If I say long exact sequence and 5 lemma, that should be the proof. But for now, we elaborate a bit on that part. So let's look at the long exact sequence. We have these compatible short exact sequences. We know naturality gives us not just the long exact sequence, but a ladder between the 2 long exact sequences associated with these short exact sequences. And let's write them down. So let's maybe start with H and B. Okay, I wanted to write the naturality of the long exact sequences yields the following commutative ladder. So it starts with H and B, then we have Hn of this complex of small simplices. Instead of Hn C star B, I just write Hn B because that's the definition of the single homology of B. But here I write again Hn of this complex. And then it goes down via the boundary homomorphism to Hn minus B and Hn minus Cu star x, and then we stop writing here. And the same for the other one, or almost the same. Now I can write Hn of x, which is the same as Hn of C star x. And here I could actually write Hn of x comma b, but okay, maybe it's clearer if I write this out as Hn of this complex and we stop again at Hn minus 1 of x. Now, the commutative diagram above by naturality gives us commutative diagram as follows. So here we have the identity, here we have the map induced by the inclusion, here the same, here the identity. Maybe I just write equal here. And here the same. And the lemma of small simplices gives us these isomorphisms now. Okay, so this is an application of the lemma of small simplices. And now we have the situation of the 5 lemma. We have 5 modules above, a row of 5 modules below. Everything commutes, and we have a map here that's surrounded by isomorphisms. And the 5 lemma gives us that this is an isomorphism.
Yeah, so these 2 consecutive isomorphisms always are applied twice, right? For degree n and for degree n plus 1, we also use these isomorphisms. They're once on the left-hand side, once on the right-hand side of the map in question.
Yeah, we really have to use that. We get the statement of the lemma of small simplices in all degrees. It doesn't help if you only have it in one specific degree for an application of this 5 lemma. All right, so this is the proof of excision, assuming we have this lemma. I won't prove this lemma in this video, but I want to give you some idea why this lemma is true. So what's the idea? The idea is based on subdivision. So this lemma is particularly easy for degree 0. So let's look at the various degrees. So degree 0, what is happening here? Well, we have a cover. Every point lies in one of the subsets. So C0u of x is the same. I'm writing too fast for the screen. It's really the same as C0x. Okay, so there we know what's going on. But for degree 1, it's already different because you might have very, very long 1 simplices. And so we have to prove that it is a homology isomorphism. For now, we look at degree 1. So we have to prove that any 1 cycle is in homology represented by a 1 cycle consisting of singular simplices that are small with regard to the given cover U. So consider such an element representing a homology class. So consider a 1 cycle in C1x. And we know what is a 1 cycle. Well, it is a linear combination of singular 1 simplices. And I'm looking now at each one of these singular 1 simplices, and I will do something to each of these singular 1 simplices to get what? To get a different 1 cycle, which represents the same element in homology, but consists only on U small singular simplices. So let's look at a picture with a cover, and just to illustrate the point, just drawing 2 elements in the cover, and so singular 1 simplex is something we know very well. And the situation could be that this is just too long to lie in one of the sets. Could be something like that. So that's our sigma, part of this linear combination of the 1 cycle. Let's give it a name. Let's call it C in C1x. Okay, and that's one of the singular 1 simplices appearing in this linear combination. That causes a problem because it's too large. But what we could do, at least in this picture, you see if we subdivide this in half.
Why are you talking about cycles at this point? Why not just chains?
Well, I'm talking about cycle because the argument is, or the statement is about homology isomorphism. Mm-hmm. So I'm saying that each homology class can be represented by 1 coming from C star U.
Okay.
For the argument, I mean, it's not really a full argument. For the heuristics, it's actually not important that it's a 1 cycle. It could be a 1 chain. All right, so if you subdivide this into halves, then somehow the midpoint would lie here. And what you see are 2 1 simplices here, which after an obvious identification you could regard as 2 copies of the standard 1 simplex. And then the restriction of sigma gives you 2 singular 1 simplices that lie really completely in one of the subsets of the cover. And therefore, the idea is to replace this sigma that causes problems by a sum. Which sum? Well, let's give this a name here. Let's call this W, this midpoint. W. And replace sigma by the sum of sigma restricted to V0W plus sigma restricted to W V1. And of course, to consider these 2 as singular 1 simplices, there is the usual identification so that we are able to regard this as singular 1 simplices. So identify the standard one with V0W, and this one in the usual way again meaning that there is an order of vertices here in this, how I write it. So the identification is always linear isomorphism, respecting the order. And then you see from the picture that if we do this to any singular simplex in this cycle C, then, well, at least we get some chain whose singular simplices are small. But it might not always be like that situation where you just have to divide at the midpoint and you get what you want. It could also be that you are in the following situation. Maybe a bit more. So if you're in this situation, that your simplex sigma looks like that, then you might have to repeat what we did before. So the midpoint would land here, but it's still too big, so you have to repeat in each of the two segments this dividing into halves again, and then let's draw it favorably for our situation, like that.
The funny thing is that in the application, this actually won't even occur, right? Because the covering we're applying it to consists only of two subsets.
That's true.
That's true. But anyway, yeah.
No, but I mean, the subsets could look very different, right? I mean, I drew them as balls.
Yeah.
They could be like...
Yeah, I'm just saying, I mean, in this picture, you're assuming you have three subsets.
Yeah. No, but the lemma of small simplices is for arbitrary covers. Mm-hmm. All right. So let me write, maybe you might have to repeat this. If there is such a situation, and then of course what you do is you already replace sigma by this sum of two simplices, and then replace further each of the parts by a sum again, so that in the end we end up with a sigma being replaced by a sum of four singular simplices. And again, you have to, depending on how fine this cover is, how the situation looked like, you might have to repeat this process further and further, but after a finite number of steps, your singular simplices will be small enough. And that's a replacement that you do with this one singular simplex sigma in this linear combination that is the chain in C1x that we started with. And if you do that, then you get a new chain, a new one chain. So the resulting, you have to repeat this several times. Okay, that's actually, I completed this to a sentence. You might have to repeat this several times. And then after a finite number of steps, you get a resulting chain C prime. So the resulting chain C prime, which is in C1x, is not just in C1x, but it's is actually in C1 ux, and I claim this is homologous to C. And what I mean by that is they represent the same homology class. So representing the same homology class means that difference of these two is a boundary.
So it's homologous after re-embedding the U small chains into all chains. Yeah.
Yeah. Mm-hmm. Yeah. You're very precise, but that's good. Right, so we have to find such a two chain. So B is a linear combination of singular two simplices, so that the difference is this boundary of B. So where B is in C2x, and elements in C2x are linear combinations of singular two simplices. And instead of giving a formal proof now, that's something that we reserve for a separate video, I will give you at least an indication where these singular two simplices come from. Okay, they have to have a source, and this is easily seen, at least in this small degree. And let's just look at the situation where we have subdivided just once. So we have this situation again. We have this W in the middle. We replace the singular simplex sigma by the sum of the two coming from these two halves. And somehow I should at least explain how a singular two simplex arises from this situation. And the singular two simplex can be drawn here. So singular two simplex is something like that. Usually we denote the vertices also by V0, V1, and V2. It's always a bit awkward if you have simplices of different dimensions, because then we have the same label for different vertices. So let's just, for the purpose of this, call it now E0, E1, E2. And the singular two simplex that I want to consider comes as a composition of an affine linear map of this two simplex to the one simplex, followed by sigma. So I will explain a linear map here, and the composition will define rho, a singular two simplex. Okay, what is the map? Again, this map here is a linear map, linear affine map, and I just have to say where do the vertices go to explain this map. And E2 will go to V1, and E1 will go to W, and E0 will go to V0. That's the linear map. And now I want to compute the boundary of this two simplex. So if you look at the image of this two simplex, it's somehow degenerated, right? It's not really something two-dimensional in X, because it gets first mapped to something one-dimensional, and then via sigma to X. Nevertheless, it's a highly degenerate two simplex, but it is a singular two simplex that we can consider, and its boundary can be easily computed. It's just our usual formula. First drop E0, then you have this, then minus dropping E1 plus dropping E2. Let's just look what we got. So rho restricted to E1, E2 is just the restriction of sigma to W and V1. So this is sigma restricted to W, V1, minus E0, E2 is the original simplex sigma. I mean, let me now write sigma V0, V1, but that's just sigma. That's the whole singular one simplex we started with. and then finally plus sigma restricted to V1W. And now let's just regroup everything. Somehow this row is one of the singular two simplices that in general is part of this chain B we're looking for. In our situation, and our chain C I started with just consisted of, I was just focusing on one singular one simplex. And if I rewrite this now as just interchanging the last two terms, then we see that in our argument above, this corresponded to C prime and this corresponded to C, or at least one singular simplex in C and its replacement in C prime. And well, you can do this now to every singular simplex. You can repeat the construction. I think one sees from this that at least in degree 1, we can now replace, without changing the homology class, a cycle by a U small cycle. What do you do in higher degrees? Let's at least mention what you're doing. Again, in higher degrees, the subdivision is a bit, well, it's a bit different. Here you just subdivide an interval. You have to explain what you mean by subdividing a standard simplex to make the restrictions of this singular simplex to this smaller simplices U small. So in higher degrees, you define inductively a subdivision procedure, and what you do is, if you have it, let's do it for two simplex, which is you want to make this smaller, then you first look at its boundary, and there you already know what the subdivision procedure is. It's just subdividing into halves. And now to define the subdivision in degree 2, you just take the barycenter and connect to all the points that are around. And then you see a bunch of 6 standard simplices after the obvious identification, and the restriction of sigma to these 6 standard simplices gives you 6 singular simplices whose sum, and now you have to choose signs appropriately, is a replacement for the sigma. And then again, you might have to repeat this. And in higher degrees, there is something similar. But if you write down the details of that construction now, it becomes really important how you choose the signs and everything. And this is something that we do in a separate video. If you just want to know why excision works, I think that's all you want to know. Mm-hmm. That's the basic idea, and how we get from the lemma of small simplices the original statement.
So except that maybe one problem with this construction becomes already apparent at this point. Maybe you can scroll up again the picture where you had 2 overlapping circles and the one simplex embedded into the 2, which you made small. It should be farther above, a little more, this one, yeah. So if you want the subdivision procedure to induce anything in homology, yeah, you have to make sure that it defines a chain map from all chains to U small chains. Yeah, and if you do this with this very simplex that's drawn there, mm-hmm, then what does the chain map condition say? It says that, well, if I first subdivide it and afterwards take the boundary, I should end up at the same thing as if I had first taken the boundary and afterwards subdivided. But as you already pointed out, there's no need to subdivide 0 simplices, right? So if you first take the boundary and then you subdivide, you do nothing, you end up with the 2 endpoints of this S-shaped curve. But on the other hand, if you had first subdivided, yeah, and then taken the boundary, you will have 3 points. Yeah, so you do not end up at the same thing.
Well, but they cancel. So if you take the boundary of delta 1, sorry, if you take the boundary of that thing, so you take the boundary after subdividing, then you get this W, but with different signs.
Got it.
So the W cancels away, and you end up in the boundary of that just with V0 and V1.
Okay. Yeah, you're right. So in this very case, the problem doesn't yet occur.
Right. And in higher degrees, and that's why. So it's easy to draw this picture with subdividing the two simplex, but then you have to somehow inductively, carefully choose the signs of your construction so that it really becomes a chain map.
Yeah, because in that case, it's not clear how many times you have to subdivide until it is U small, right? So if you have, say, a triangle in such an overlap of circles, then it might be necessary to divide the full triangle more times than you would have to subdivide the faces of that triangle. So this is what I was thinking about.
But you're confused because you're thinking of the stronger statement where I said, well, in fact, it's a chain homotopy equivalence, this inclusion. Right now, I'm just arguing that it's a homology isomorphism. So I can look at individual homology classes, cycles, and do something to them. I'm not assembling what I'm doing to individual classes to a global chain map.
Okay.
But so you're right. If you prove that it's a chain homotopy equivalence and you want to define this chain homotopy inverse, then it becomes slightly more complicated. And the issue might arise that you're alluding to that, yeah, you might have to subdivide more often on the whole thing than on the boundary, and somehow you have to write it down consistently.
Well, now I really see what the shortcut is here, that this is the issue you don't have to take care of if you only want the homology isomorphism. Okay, all right.